All right, so today we're diving into function space learning rates. And this paper kind of tackles a question that's been bugging me for a while, like how do the changes that we make to a neural network's parameters, how do they actually affect the output function?
Yeah, it's a really fundamental question. And this paper introduces this idea of layerwise function space learning rates. And maybe just to be clear, these aren't the typical learning rates that we use during training to, adjust the parameters. Instead, they measure the magnitude of the change in the network's output function due to updates in specific parameters tensors.
So it's not just about like seeing the parameters change, but it's about actually seeing how much that change ripples through the network and changes its behavior.
Yeah, exactly. It's like, instead of just seeing the individual brushstrokes of a painting, you're looking at how each brushstroke contributes to the overall composition and the final image that comes out of it.
I like that analogy. It makes it much more visual. But how do you even measure these function space learning rates? I mean, that sounds like it could be incredibly computationally expensive.
Yeah, that's a great question. And so this is where the authors, I think, got really clever. They devised a Monte-Carlo estimation method that only requires one additional backward pass. So the overhead is really, really minimal.
Okay, so we're not sacrificing efficiency for these insights. That's good. But why should AI researchers care about these function space learning rates? What are some of the practical applications?
Well, there's two key areas where this shines, I think. The first is that it gives us this new lens to analyze how standard optimizers like Atom actually work. So, instead of just observing the parameters changing, we can now see how different parts of the network actually contribute to the functional changes during training.
So we can actually see which parts of the engine are driving the car, so to speak, not just, watching the gauges.
Exactly. We can kind of pinpoint which layers are actually doing the heavy lifting in terms of shaping the network's learn function. The second area is, and this is maybe a game changer for people working with large models, it's all about hyperparameter transfer.
Okay, hyperparameter tuning is like the bane of my existence, so I'm all ears.
I hear you. So the authors introduced this method called FLeRM, which stands for function space learning rate matching. And the idea is you train a small base model, and then you record these function space learning rates during training.
Okay.
And then you can use that information to automatically adjust the learning rates for larger models to try and maintain consistent function space updates as you scale up.
Oh, so it's like instead of starting from scratch with a new model size, you're using those insights from the smaller model to guide the learning process in the larger one.
Yeah, exactly. And they show that this works for various scaling factors like model width and depth, and even for things like LoRa rank, which is used for fine-tuning very large language models. And, they're able to achieve comparable performance with much less tuning effort.
Now, that's what I call efficiency. This is still pretty abstract to me. Can we see how these function space learning rates actually play out in actual architectures? Like, what does it look like?
Yeah, definitely. So they look at ResMLP and transformer architectures, and they show how these rates change over time, even with a fixed learning rate schedule. So there's this kind of implicit scheduling happening within the network as it learns.
So even though it's setting like a static learning rate, different parts of the network might be learning at different speeds in function space.
Exactly. And even more interesting, I think, is that they find that different layers actually have drastically different function space learning rates. So, for example, in transformers, they showed that the second feed-forward weight matrices in the self-attention layers, those actually have the biggest influence on the learned function, even more so than the readout layer.
Really? I would have thought that the readout layer being, responsible for the final output, that would be the most influential.
Yeah, you would think so, right? But this analysis shows that sometimes the most influential layers are actually hiding a lot deeper in the network than we might expect.
That's pretty counterintuitive.
Yeah.
It really highlights how this function space perspective can uncover like hidden relationships within these complex systems.
And that's just the beginning. It turns out that, how these function space learning rates change, it also depends on the specific architecture. Even things like the layer normalization scheme you use in transformers can have an effect. So every design choice kind of leaves a unique fingerprint on the learning process.
Oh, wow. My mind is officially blown. This is way more than just like a new metric or something. This is like a fundamentally different way of looking at how neural networks learn.
I completely agree. It's a real paradigm shift. And the implications are pretty huge.
Yeah. Okay. Before we get too carried away here, let's take a moment to process all of this. But when we come back, I want to dive deeper into these applications, especially this FlareM method, and explore what the implications are for the future of AI research. Sounds good to me.
Okay, so I want to unpack this FLeRM method a little bit more. You mentioned that it could be a game changer for large models, but I'm still kind of wrapping my head around how it works in practice.
Yeah, so imagine you have a small trained ResMLP model, maybe with like 4 hidden layers, like they use in the paper. And you've already measured the layer-wise function space learning rates during training.
Okay, so we have this record of how those rates evolved in that specific model. Now, how do we actually apply that to a larger model?
Right, so let's say you want to scale up the model by increasing its width. Traditionally, you would have to experiment with different learning rates to find what works best for this new size. Right, but with FLeRM, you can use those function space learning rates from your small model as a guide. And it kind of automatically adjusts the parameter space learning rates in the larger model to try to keep those function space updates consistent.
So the larger model is essentially like mimicking the learning trajectory of the smaller model, but in function space rather than parameter space. Yeah, that's the idea. And it's not just for width scaling. They show that it works for depth scaling changes in initialization scale. And even when adjusting the LoRa rank for fine-tuning those massive language models.
Hold on, back up a second. How does FLeRM apply to LoRa? I thought it was about scaling up the entire model.
Right. So with LoRa, you're only training a smaller set of adapter parameters, right? The pre-trained model weights are frozen. It's a very efficient way to fine-tune for specific tasks, but the optimal learning rates can kind of shift when you change the rank of those adapters.
Makes sense. You're essentially altering the model's capacity, so that probably affects the learning dynamics.
Exactly. And so that's where FLeRM comes in. You can measure the function space learning rates from a base model with a specific LoRa rank, and then when you scale up to a higher rank, FLeRM can help automatically adjust the learning rates. So it really streamlines that process considerably.
That's really clever. But let's go back to those differences in function space learning rates across layers. What are the implications there? I mean, it seems like a pretty big deal.
Yeah, I mean, I think it really challenges our assumptions about which parts of the network actually matter most for learning, right? We tend to focus on the output layer.
Yeah, it seems intuitive that that's where like the final predictions are coming from. That's where all the action is.
Right, exactly. But this analysis shows that sometimes the most influential layers are actually hiding much deeper in the network. Remember how in transformers, those second feed-forward weight matrices and the self-attention layers actually had a bigger impact than the readout layer? That's huge. We need to rethink how we approach things like regularization and pruning.
So instead of just applying like a one-size-fits-all approach, we need to consider those function-space learning rates and maybe tailor our strategies accordingly.
Exactly. For instance, when you're using weight decay, you might want to apply different decay rates to different layers based on their actual impact on the learned function. And for pruning, we might want to prioritize preserving those connections that have higher function space learning rates. It's all about working with the network's intrinsic hierarchy.
This is giving us like such a deeper understanding of the network's inner workings. It's like we're finally learning to speak its language.
And I think that's just the beginning. You know, imagine what we could do with this knowledge. Maybe designing entirely new architectures, or even more efficient optimization algorithms that are finely tuned to function space.
Okay, my mind is officially blown. This concept of function space learning rates has opened up like a Pandora's box of possibilities.
It all stems from this really simple but profound shift in thinking, right? Instead of focusing on the changes themselves, we're focusing on the functional impact of those changes. We're kind of stepping back from that microscopic view of individual parameters and looking at the bigger picture.
We're seeing the forest instead of getting lost in the trees. And by understanding the contours of that forest, I think we can navigate it much more effectively. This is going to change the way I approach model development from now on.
I think it has the potential to change the field as a whole. It's a really exciting time to be working in AI.
I couldn't agree more. Well, before we dive into the future implications of all of this, let's take a quick moment to gather our thoughts. When we come back, I want to explore those potential research directions that this paper kind of opens up and what it all means for the quest to build truly intelligent machines.
Sounds good to me.
All right, so let's talk about the future. This whole function space perspective feels like it's like cracked open. A whole new world of possibilities for AI research. Where do we even begin to explore?
Yeah, it's a vast and fertile landscape, I think. This paper has really laid some serious groundwork for, I think, a new wave of innovation. One thing that comes to mind immediately is how we can use these insights to really supercharge transfer learning.
Okay, now you've got my attention.
Yeah.
Transfer learning is already incredibly powerful. How do we take it even further with this?
Well, imagine being able to transfer not just learning rates, but also the actual functional changes that a base model has learned. So instead of starting from scratch with a larger model, you'd kind of give it a head start. It's almost like saying, hey, you've already grasped these fundamental patterns, now build upon them.
That's mind-blowing.
Yeah.
It would be a game changer in fields where data is scarce or expensive to collect, like medical imaging or scientific research.
Absolutely. And beyond knowledge transfer, I think this function space view could help us design more robust and reliable networks, which is becoming increasingly crucial as AI, becomes more and more integrated into our lives.
When you say robust, what do you mean exactly?
Well, one of the Achilles heels of neural networks is their sensitivity to even small parameter changes. You tweak things a bit and suddenly the performance can go haywire.
Yeah, it can feel like a bit of a tightrope walk sometimes.
Yeah.
Is this function space approach kind of the safety net we've been missing?
It could be. By understanding how those parameter changes translate to functional changes, we might be able to design networks that are inherently less sensitive to those perturbations. So it's about building systems that can kind of maintain their core functionality even under pressure. Think about applications where reliability is absolutely paramount, like self-driving cars or medical diagnosis.
That's a really critical point. It's not just about performance anymore. It's about building AI we can truly trust.
Exactly. And let's not forget those really fascinating dynamics we observed with the function space learning rates changing over time. I think there's a goldmine of information hidden in those patterns.
What kind of secrets are we talking about here?
Well, for instance, those shifting rates might reveal how different optimization algorithms navigate that lost landscape. We might be able to see why some get stuck in local minima while others gracefully escape. Imagine being able to tailor algorithms specifically to the challenges of function space, achieving faster convergence and better solutions.
Okay, I am officially on board the Function Space Express.
Huh.
This paper has been a wild ride.
Yeah, and we've only just scratched the surface. I think function space learning rates has really thrown open the doors to a whole new dimension of AI research. Who knows what incredible discoveries await us as we venture deeper into this realm of function space.
Well, sadly, our deep dive has to end here. But this is a conversation I know we'll be revisiting for years to come.
Yeah.
To everyone listening, keep your eyes peeled for developments in this area. It's going to be huge.
Absolutely. And remember, don't be afraid to challenge assumptions and think outside the parameter box. Sometimes the most groundbreaking discoveries come from simply shifting our perspective.
That's a perfect takeaway. Thanks for joining us on this incredible journey. Until next time, keep learning, keep exploring, and keep pushing the boundaries of what's possible with AI.